Design of Zookeeper. Preface. Content of this lecture. In this lecture, we will discuss the design of Zookeeper, which is a service for coordinating processes in a distributed application. We will discuss the fundamentals, the design goals, architecture, and the applications of Zookeeper. Zookeeper is also known as Apache Zookeeper, which is an open source foundation. So, it is available free to be used for the open communities. Zookeeper, why do we need it? So, Zookeeper provides the coordination service. What is the coordination? We can understand by looking up this particular picture. There will be a traffic congestion at the intersection. So, if there is a coordination, then there will not be any such congestion and there will be a smooth flow of the traffic. Similarly, here in our scenario of the big data computing, we have the hundreds and thousands of cluster nodes wherein the processes are executing. These cluster nodes are coming up and going down. That means they are prone to the failure, and different applications require to be run on these nodes. Therefore, for the smooth way of resource allocation in a fault tolerant or a reliable manner, there is a requirement of coordination service, and Zookeeper is used for that purpose for designing of different big data applications and the libraries. We will see in this part of the discussion. Having understood what a coordination is and how important the coordination is, now we have to understand in another scenario, which is of the master slave relation of a distributed system. Here most of the systems like HDFS has one master and a couple of slave nodes, and these slave nodes will report to the master. What happens if the master fails? The entire system will collapse to work. The fault tolerant distributed systems wherein between master and slave there is a coordination service which coordinates between the master and slave processes running on different nodes. So, the irrespective of the node failures, the coordination service will assign the nodes to these masters, and therefore, a fault tolerant distributed system can be envisaged using such a coordination service. So, this coordination service is very much required to achieve this fault tolerant coordinated view of any application in a distributed environment. So, real distributed fault tolerant system have a coordination service, that is the master and a backup master. So, if a master fails, then the backup master takes over, and this particular taking over of backup master as the master is to be monitored and decided by the coordination service. So, therefore, the master and the slave can be used in an application irrespective of the faults. So, if the primary, that is the master primary fails, then the backup can be taken up to ensure the fault tolerant distributed system. Here in this example, the coordination service is the Zookeeper, which provides the coordination services to achieve the fault tolerant distributed system. This particular coordination service has to be ensure that it should not lead to a deadlock and also not suffer from the race conditions. So, and it ensures that deadlock can be prevented. Deadlock should not happen in any of the case, and also it should not face the race conditions. To understand these two terms, what do you mean by the race condition? We can see through this particular example. So, when two processes are competing with each other causing data corruption, for example, person A and person B together, they want to update the same variable, that is the bank account, which is having the current value 17 at the same point of time with the value 1, then what will happen is they may read the variable 17 and update at their end and finally write back the values. So, instead of two increments, only one increment is now taken into the effect. Therefore, together the two processes which are competing may cause the data corruption here in this example which is shown. This condition is called a race condition. So, as shown in the diagram, two persons are trying to deposit 1 rupees online onto the same bank account. The initial amount is 17 rupees. Due to the race condition, the final amount is written as 18 rupees instead of 19. So, therefore, this condition is called a race condition, where competing processes which are writing the or which are accessing the variable may cause the race conditions and therefore may corrupt the data. This has to be avoided in the coordination service. Why? Because multiple servers, multiple systems, they are trying to access or trying to run the same service. Therefore, this race condition may be a possibility, and the coordination service has to be such that race condition should not occur. Another problem is about deadlock. So, when two processes are waiting for each other directly or indirectly, and none of them is basically able to progress, then it is called a deadlock. So, here in this example, set of waiting processes 1, 2, 3, they are said to be deadlock if they are waiting for each other for the resource allocation, and none of them are finishing for the others to complete. Hence, this circularly waiting processes are said to be in a deadlock. So, in our scenario, in a distributed computing where different servers are running different processes and they may be communicating with each other, they may also suffer to this particular problem, which is called a distributed deadlock problem. So, hence the situation of coordination service should be such that it should not lead to a deadlock. So, let us see some of the example of the coordination service in a distributed system for big data computations. Let us understand the email processors and how these email processors avoid reading the same email using the coordination service. Suppose there is an inbox from which we need to index emails. Indexing is a heavy process and might take a lot of time. Hence, we have multiple machines which are indexing the emails. Every email has an ID and you cannot delete any email. You can only read an email and mark it as read or unread. Now, how would you handle the coordination between multiple indexer processes so that every mail is indexed? That is shown here in this particular picture. So, if the indexers were running as multiple threads on a single machine or a single processor, then it would be easily handled with the help of synchronization constructs of a programming language. But since there are multiple processes running on multiple machines, we need to coordinate. That is, we require a central storage kind of scenario implemented on a distributed system, which is nothing but a coordination service. So, this central storage would be safe from all concurrency related problems. This central storage is exactly the role of the coordination in the Zookeeper. So, again, what is the coordination? That is about group membership, that is the set of tasks on the data node belong to the same group, that is also a coordination service. To elect a leader between the primary and the replicas, that also is a coordination service. Then dynamic configuration, that is multiple services are joining and communicating, and there that is why common configuration is required to be maintained, wherein the active servers are to be registered, is also called dynamic configuration and is a part of coordination service. Status monitoring, where monitoring of various processes and services in a cluster is maintained dynamically, is also a coordination service. Queuing, that is one process is embedding and the other is using, that is called coordination service. Barriers, all the processes showing the barriers and leaving the barrier, is also a coordination service. Critical sections, where processes go into the critical section and then they may leave the critical section so that others can enter into the critical section. So, this kind of critical section is also a kind of coordination service. So, what is a zookeeper? So, having understood the coordination service, zookeeper is a highly reliable distributed coordination kernel which can be used for distributed locking, configuration management, leader election, work queues, and so on. So, a zookeeper is a replicated service that holds the metadata of distributed application. By meaning to say the replicated service means that particular service runs on the clusters which is consist of multiple nodes or multiple server machines. That is why it is called the replicated service. So, how that is all done in the zookeeper, which is the replicated service on one hand, while providing the centralized configuration service, that is the coordination service, that is the design goal of the zookeeper, which we are going to cover. So, the key attributes of such a data which the zookeeper requires to maintain in the replicated services are: the size of the data is small and the performance is very sensitive and it is dynamically changing, and it is also very critical to manage in the coordination replicated service by the zookeeper. So, in a very simple word, the zookeeper is a central store of key value pairs using which the distributed systems can coordinate. Since it needs to be able to handle the load, the zookeeper itself runs on many machines. So, the zookeeper exposes a simple set of primitives. It is very easy to program, uses the data model like the directory tree, and it is used for synchronization, locking, maintaining configuration. So, the coordination service should also not suffer from race condition and deadlock, though it has to be providing the synchronization, locking, and maintaining the configuration as a service. That is, the zookeeper does this, and it uses, to do this, it uses a data model which is like a tree, directory tree, and it also has a very easy program interface so that the programmers can use it for designing their own distributed application for big data computation. And it also exposes a simple set of primitives that we will see. So, the first design goal of zookeeper is the simplicity. So, it has the shared hierarchical namespace which looks like a standard file system of a Unix. So, the namespace has the data nodes, and these data nodes are known as Znodes, which differentiates from the other type of the data node usage. So, the data is kept in memory and will achieve high throughput and low latency numbers. So, high performance is one of the important features of providing the simple service that is used in the large and distributed system, and it is also highly available. That is not a single point of failure it suffers, and it also strictly orders the access, that is by providing the synchronization. So, the second goal of the Zookeeper is the replication or a replicated service. So, here the Zookeeper runs on the ensemble of servers. So, here we have seen there are 5 different servers. It can be many more also which runs the Zookeeper service. So, it is an ensemble of servers. So, it is not one server on which the Zookeeper will run, but it is an ensemble of servers on the Zookeeper will run. So, all the servers have the copy of the state in the memory, and now since all servers have the same state, therefore, leader will be elected at the startup and at all the time. Let us say this is the real leader and all others are the followers. So, the leader is elected at the startup, and at all point of time a leader is always elected to run this Zookeeper service. Now, the followers service, the clients, all the updates go through the leader, meaning to say that if there is a write operation by the client, it has to go through the leader, whereas the read operation by the client can be done through any of these available servers in the ensemble. So, therefore, it is written that the followers service the clients, but all the updates has to go through the leader. Updates in the sense the write operations has to be channeled through the leader, whereas all the read operations can be performed or can be serviced to the client from any of the followers. Therefore, update responses are sent when a majority of the servers have persisted the change. So, here we need the majority, we need 2 f+1 machines to tolerate f failures. So, this concept can be understood here in this diagram, that you can see that the client can be connected to any of the servers, whether it is follower or it is the leader. But as far as read operations are concerned, the client can be serviced by any of the follower servers. As far as the write or update operation is concerned, it has to go through the leader elected, and out of these servers at this point of time, this particular server is denoted as the leader. So, here we have the set of servers. They will know each other and they will keep in memory image of the state, and also maintains the transaction log and snapshots persistently. Whereas the other, this is one such entity in the Zookeeper. The other entity is called a client. So, the client keeps a TCP connection, gets a watch events and sends the heartbeats, and if the connection breaks, they will connect to a different servers. So, these are the client's activity in this replicated service of Zookeeper. Third important goal of Zookeeper is about the ordering. So, the Zookeeper will timestamp each updates with a number. So, the number is nothing but it reflects the order of the transaction, and it is used to implement the high level abstraction such as synchronization primitives. We will see this aspect in more detail in the further slides. Now, fourth design goal is about the speed, which is fast. So, it performs best when the reads are more common than writes at the ratio of around 10:1. So, at Yahoo, where it was created, the Zookeeper, the throughput of the Zookeeper cluster has been benchmarked at over 10,000 operations per second for the write dominant workloads generated by hundreds and thousands of clients. Let us see the data model. The way you store data in any store is called data model. Think of it as highly available file system. In case of Zookeeper, think of a data model as if it is highly available file system with a little differences. Here in this file system of Zookeeper, the nodes are called Znodes, where we store the data in an entity which is also called as a Znode. The JSON data, the data that we store should be in the JSON format which JavaScript object notation follows, and it has the append operation. So, Znode can only be updated, it does not support the append operation. So, the data access here is, that is the read and write operations, they are atomic. So, read and write operation is atomic operations, meaning either it will be full or would throw an error if failed. Therefore, in no intermediate state like half written is possible in the atomic node, and Znode can have the children's. So, again we are repeating that no append operation. So, Znode can only be updated, it does not support the append operations in this particular scenario. So, here we can see that the Znode inside the Znode will make like a tree structure, where the top level Znode is the root node, which is the top level Znode, and let us say that then child is, let us say, a Znode of this top node zoo, and this is called now the duck, and so on. So, there will be a hierarchical way these Znodes will be organized in the namespace. So, it provides the data model of the hierarchical tree structure to support the namespace. So, Znode has various types. There are two different type of Znodes. One is called persistent. Such kind of Znode will remain in Zookeeper until it is deleted. This is the default type of Znode. To create such a node, you can use the command create /name of my Znode my data. Ephemeral type of Znode, ephemeral nodes gets deleted if the session in which the node was created has disconnected. Though it is tied to the client session, but it is visible to the other users. So, an ephemeral node cannot have the children, not even the ephemeral children's. So, there are two different type of Znodes, persistent and ephemeral we have just discussed. So, ephemeral is related to the session, whereas persistent it will remain in the Zookeeper until it is deleted. Now, another type is called sequential, will create nodes with the sequence numbers in the namespace. The number is automatically appended, and the counters will keep on monotonically increasing. So, each node has a counter. So, here we can see that the Znode which is created has this kind of sequence numbers, and whenever the new nodes are increasing added. So, these numbers are keep on now increasing whenever the nodes are, whenever a new node is created with a sequence number. So, the architecture of Zookeeper, we can see here that Zookeeper can run in two modes. One is standalone, the other is called replicated mode. In a standalone mode, it is just running one machine, and for practical purpose we do not use this standalone mode. This is only for testing purposes and does not have the high availability, because it is running on only one machine, and if it fails, the entire operation will stop functioning. Therefore, it is only meant for testing purposes. The other mode of operation in the Zookeeper is called replicated mode. It is used for the production clusters in this mode. So, it runs on the cluster of machines called ensemble, and it ensures high availability and also tolerates as long as it ensures the majority of the machines are in active service. So, let us see the architecture, and in this architecture this Zookeeper runs in two phases. So, the phase 1 is about the leader election, which uses the Paxos like algorithm, which is called Z service. So, which is called ZOB, Z operations. So, the machines will elect the distinguished members, which is called the leader over here, which is shown here as the Zookeeper service in the phase 1, and the other servers are termed as the followers in the ensemble of servers for running the Zookeeper service. Now, this phase is finished when the majority will sync their state with the leaders, and if the leader fails, the remaining machines will hold the election and elect another follower as the leader, and this process of leader election takes only 200. Now, if the majority of the machines aren't available at any point of time, the leader automatically steps down. So, leader election has to be ensured if the majority rule follows, and therefore, the majority rule is important to functioning of the Zookeeper. Now, in phase 2, there will be an atomic broadcast, that is, all write requests are forwarded to the leader, and so the client you see here is forwarding the write request to the leader, and the leader broadcasts the updates to all the followers. When a majority have persisted the change, that is, the leader commits the update and the client gets the success response, then the protocol for achieving the consensus is atomic, and this is like two-phase commit protocol. So, the machines will write to the disk before in memory. So, now let us see in more detail about the phase 1, which is the election process in Zookeeper. So, Zookeeper is a centralized service for maintaining the configuration information. Now, Zookeeper uses a variant of Paxos which is called ZAB, that is Zookeeper Atomic Broadcast. Now, Zookeeper needs to keep the leader elected at all point of time. How that is leader is elected, we will understand the complete process in the Zookeeper. So, each server will create the new sequence number for itself, and this particular sequence number is stored in a file. So, let us say that the sequence numbers are the node IDs, and the highest node ID seen so far from the Zookeeper file system will create the next higher ID and writes it into the Zookeeper file. Now, elect the highest ID server as the leader. So, here in this example, the different servers will have their IDs and 80 and 6 and 12 and 3 and 32 and N5. Among these 6 different servers, the one with the highest ID is an 80, and it is now, after this election, it will be elected as the leader or the master. Now, what about the failures? Now, during the election or after the election, that the master may crash. So, one option is that everyone monitors the current master directly via the failure detectors. So, that means in normal cases, leader election is not happening again and again, even if the master fails. So, every other node monitors the current master, and whenever it detects that the master is failed, it will initiate the election. That means, if they initiate the election, it will lead to a flood of lot of messages and too many messages. Therefore, this option of whenever there is a failure, everyone start electing the leader, this will require a flood of messages. Therefore, we will see a second option which is implemented in Zookeeper, wherein the each process monitors its next higher ID process. For example, process number 32 will monitor process number 80, and 80 will monitor 3, and 3 will monitor 5, and 5 will monitor 6, 6 will monitor 12, and 12 will monitor 32. So, each process will monitor its next higher ID process. Now, if that successor to which a process is monitoring it detected as the failed, and if that failed process happens to be the leader, then that particular process who has detected this leader to be filled becomes the new leader. So, there is no leader election required here in this case of Zookeeper. Otherwise, then it will wait for a timeout and check the successor again. So, therefore, what about the IDs conflict? What about if the leader fails during the election? In both these cases, to handle these cases, the Zookeeper does this election using two-phase commit protocol. So, Zookeeper runs after the sequence ID, and this particular protocol used to commit the leader. So, leader will send the new leader message to all of the other processes, and each process will respond with the acknowledge to at most one leader, that is one with the highest process ID seen so far. The other processes will respond as an acknowledgement, allowing that particular process to become the leader. Now, leader awaits for the majority of acknowledgements and then sends the commit to all. On receiving the commit protocol, on receiving the commit message, the process updates its leader variable, and it ensures that the safety is always maintained in this two-phase leader election protocol. Let us see the election process demonstration in Zookeeper. Now, if you have three nodes A, B, C with leader elected as A node shown on the left side of the diagram, and if A dies, will someone become the leader? Someone, that is the remaining B and C, will become the leader. So, if A dies, then B and C, which becomes the majority of 3, that is 2 out of 3 is the majority. So, majority survives, hence out of B and C, one will be elected as the leader. So, the answer is yes. That means either B or C can become the leader. Why? Because even after the failure of A, the remaining node set remains in the majority. Now, what about if two nodes are failed? It is not only one, but two nodes are failed. So, the remaining one is node number 1 out of 3. 1 out of 3 is not in a majority. Therefore, if you have 3 nodes and 2 of them dies, then will the C becomes the leader? The answer is no. No one will become the leader. Why? Because C becomes the follower, and the reason is that the majority is not available if 2 nodes dies. Therefore, the leader election will happen as long as after the failure the majority of the server is surviving. Now, let us see why the majority is important feature or important parameter in the leader election. So, imagine that you have an ensemble of servers which are spread across 2 different data centers. So, this example shows that you have 6 servers which are spread across 2 data centers, that is 3 on one data center, and remaining 3 out of 6 will be on the other data center. Now, if let us say there will be a disconnection which is the network disconnection which connects these 2 data centers. So, imagine the network between the data center got disconnected. Now, if we did not need the majority of electing the leader, then what will happen, that every data center will be electing one leader, and therefore, in this particular scenario there will be 2 leaders appointed, and in this case there will be violation of leader election. There cannot be 2 leaders at the same point of time. Hence, therefore, the majority is required to avoid this kind of scenarios. Now, we will see about the sessions which are maintained in the Zookeeper. Now, let us try to understand how the Zookeeper decides to delete the ephemeral nodes and take care of session management. So, a client has the list of servers in the ensemble, and it tries each until it becomes successful, and the server creates a new session for the client. A session has the timeout period which is decided by the caller. So, if the server hasn't received the request within a particular timeout period, it may expire the session. On session expiry, ephemeral nodes are lost. To keep the session alive, the client sends the ping, that is the heartbeats, and the client library takes care of heartbeats. Sessions are still valid on switching to another server. So, failover is handled automatically by the client, and applications can't remain agnostic of the server reconnections because the operations will fail during the disconnection. So, this is automatically handled by the Zookeeper. Let us understand that when a new Zookeeper process is starting about connecting to it, then it will watch the events and keep the state synchronized with the connected with the clients, that is called connected. So, the Zookeeper, when it is closing the connection, then it will be closed, and in between it will watch the events keeper state, and this particular when it is expired, then it will send that the watch event state is disconnected. So, these state transitions are handled. Now, let us see the use case where many servers are available, and how the coordination service will ensure the availability of server to any applications which is running on the server. So, now let us see that there are many servers which can respond to your request, and there may be many clients which want this particular service to run. So, the client want to know which of these servers are alive at a particular point of time, and directly every client instead of maintaining the list of servers which are active and keep on updating at their level, instead of that, let us keep a coordination service which is called a Zookeeper. Now, Zookeeper will coordinate between all the set of servers and between the set of all different clients. So, from time to time some of the servers will keep going down. How can all client can keep track of these different servers? So, the available servers will be now maintained not by the client, but by the service which is called a Zookeeper. Now, let us see, let us take the case of two servers and a client. So, the two servers duck and cow are created by their ephemeral nodes under /server which is shown over here. The client would simply discover the alive servers cow and duck using the commands /servers. Now, after some time the server called duck is now down. So, both are now ephemeral nodes which are now created with the name duck and the cow, and after some time this time flows down. After some time this particular server dog got killed. So, then this particular client, when it again accesses /servers, it will see only that cow is visible. So, earlier it was duck and cow, two servers were alive because they have created an ephemeral nodes. So, a server called duck is down, the ephemeral nodes will disappear from the /server Znode, and hence the next time the client comes up and queries, it will only get the cow. So, the coordinations has to be made heavily simplified in this Zookeeper and made efficient also because of the Zookeeper. Now, Zookeeper guarantees the sequential consistency, that is, the updates from any particular clients are applied the order in which these updates are done, that is called sequential consistency. Now, second property which the Zookeeper guarantees is about atomicity, which says that the updates are either completely successful or null, that is, either it is fully done or it is not done, that is called atomicity property to ensure the consistency of the data set. So, single system image, that is, a client will see a single view of the system. So, when a new server will not accept the connection until it has been caught up. So, therefore, every client, so the clients will see the same view of the set of systems or the state variable here in case of Zookeeper. Now, another thing which guaranteed by the Zookeeper is called durability, that is, once the update has been successful, it will persist and it will not be undone. Another part is called timeliness. So, rather than allowing the client to see the very stale data, the server will in this case will shut down. So, these are some of the operations of the Zookeeper create, delete, exist, ls, get ACL, that is access control list, set ACL, get data, set data, sync. We will not go in more detail, and we will see, we have just shown you the type of operations, commands which are supported by the Zookeeper, which are very simple. Now, multi updates, here the batches together supports the multiple operations, either all or none is done in entirety, and possible to implement the transition in this scenario, and others will never observe any inconsistent state. Different APIs are available, and out of them 2 core APIs are Java and C, and other contributions are Perl, Python, REST, and for each building the synchronization and asynchronous things are available, which are there in. Now, another part which is available in the Zookeeper is called watches. So, clients to get notifications when a Znode changes in some way is done through the watches. So, watchers are triggered only once. For multiple notations, they have to re-register. So, watch triggers are available in Zookeeper, and this is used to get the notifications for the clients. So, whenever there is a Znode changes in some way, the clients will get the notification. So, watch triggers. So, the read operations which exist here is to get children, get data, may have watches which are triggered operations. So, watches are triggered by the write operations such as create, delete, set data. Then there is an access control list of operation which do not participate in the watches. So, watch of the following are triggered, that is exists, create, delete, or its data is updated in the Znode, then it gets triggered using exists command. Now, in the get data, that means when in the Znode the operation is deleted or it has the data updated, then using this particular get data, it will get the trigger. Similarly, when a Znode gets deleted or its any of its children is created or deleted, then using get children, the watch triggered is triggered using get children. So, in access control list determines who can perform certain operations on it. So, access control list is a combination of authentication scheme, an identity for that scheme, and a set of permissions. So, authentication scheme contains the digest, that is, the client is authenticated by the username and the password, which is nothing but a digest, generates a digest. Then SASL is that the client is authenticated using Kerberos, and it will give a session ACL list, that is called SASL. IP is the client is authenticated by its IP addresses, then it is an IP. Now, use cases is that building a reliable configuration service using Kerberos. Now, another use case is the distributed lock service, that is only single process may hold the lock at any point of time. This distributed lock service is provided by the Zookeeper. Now, let us see when not to use this Zookeeper is when you want to store very big data, then the Zookeeper cannot be stored, and also when extremely strong consistency applications are required, then also it should not be used. Now, let us see some of the Zookeeper applications, and here we are going to discuss the fetching service as the Zookeeper application. So, the fetching service is nothing but, here in this service the crawling is an important part of this fetching service, which is nothing but a search engine, and in this particular service the Yahoo crawls billions of web documents. So, this fetching service is a part of Yahoo's crawler, and it is currently in the production. So, essentially it has the master processes that commands page fetching processes. So, the master provides the fetchers with the configuration, and the fetchers write back informing of their status and the health. The main advantage of using Zookeeper for fetching service are recovering from the failure of the masters, guaranteeing availability despite failures, and decoupling the client from the servers, allowing them to direct their request to the healthy servers by just reading their status from the Zookeeper. Thus, fetching service uses Zookeeper mainly to manage the configuration metadata, although it uses the Zookeeper to elect the masters, that is done through the leader election. Now, let us see another service which is called Kata. So, Kata is the distributed indexer that uses Zookeeper for the coordination service, and it is an example of non-Yahoo application. So, Kata divides the work of indexing using shards. So, a master server assigns the shard to the slaves and tracks the progress. So, slaves can fail, so the master must redistribute the loads as the slaves come and go. So, master can also fail, so the other servers must be ready to take over in case of the failures. So, Kata uses Zookeeper to keep the status of slave servers and the master. Therefore, it is called the group membership, which is done through the Zookeeper, and to handle the master failure by the leader election. So, the two aspects of leader election of Zookeeper which is used here in Kata service is called the group membership and the leader election. So, Kata also uses Zookeeper to track and propagate the assignments of shards to the client, which is maintained as the configuration management. So, three different uses of Zookeeper is used in Kata service. First is called the group membership, where it has to keep track of slave servers and the master servers, which is called a group membership. The second one is to handle the master failover, is done by the leader election. Third is that whenever to keep track and propagate the assignments of shards to the slaves, this configuration management is used as a service from the Zookeeper. Now, another Zookeeper application is Yahoo message broker. So, that is called YMB. So, this is an Yahoo product. So, Yahoo's message broker YMB is a distributed publish subscribe system. This particular system manages thousands of topics that clients can publish messages to and receive the messages from. The topics are distributed among the set of servers to provide the scalability. Now, each topic is replicated using the primary backup scheme that ensures messages are replicated to two machines to ensure reliable message delivery. The servers that make up the broker, that is YMB, uses the shared nothing distributed architecture, which makes the coordination essential for correct operations. So, YMB uses Zookeeper to manage the distribution of topics, that is done in the configuration metadata. Also, YMB uses Zookeeper to deal with the failures of the machine in the system, that is the failure detectors, and the group membership is managed using the Zookeeper and then the control system operation, and it also controls the system operation. So, therefore, we can summarize that the publish subscribe system, which is made by the Yahoo, that is called Yahoo message broker system, uses the help or uses the Zookeeper as the coordination service for to manage the distribution of the topics using configuration metadata. Then it will deal with the failures of the machine in the system using the failure detection and the group membership of the Zookeeper, and also it performs the control operation. So, this particular figure shows the part of Znode layout for Yahoo message broker system, and so each broker domain has the Znode called the nodes that has an ephemeral Znodes for each of the active servers that compose of Yahoo message broker service. So, each YMB server creates an ephemeral node under the nodes with the load and status information, providing both the group membership and the status information using the Zookeeper of the Yahoo message broker. So, this is shown here as per the layout of Yahoo message broker structure in the Zookeeper. So, here you can see that these are the different ephemeral nodes which maintains the topics and using the ephemeral Znodes in this particular scenario. So, the topics directory has the child Znode for each topics, which is managed by the YMB. These topics that is Znodes have the children Znode that indicate the primary and the backup server of each topic, for each topic along with the subscribers of that particular topic. So, these are the subscribers, and these are the primary and the backup Znodes. So, every topic is maintained as the so each topic have the child Znode that indicates the primary and the backup servers for each topic along with the subscriber of that topic. So, the primary and backup servers, that is Znode, not only allows the servers to discover the servers in the charge of the topic, but also manages the leader election and server crashes. So, more detail of Zookeeper we can see through this particular paper written by Zookeeper, weight free coordination for internet scale systems by Yahoo people. So, conclusion, the Zookeeper takes a weight free approach to the problem of coordinating processes in the distributed system by exposing the weight free objects to the client. So, Zookeeper achieves throughput values of hundreds and thousands of operations per second for read dominant workloads by using fast reads with the watches, both of which are served by the local replicas. So, in this lecture we have discussed the basic fundamentals, design goal principles, architectures and applications of the Zookeeper, which is a centralized coordination service and which has these particular properties such as the use cases which we have seen about. We have seen the use cases of the Zookeeper as the group membership, where the set of nodes, where set of data nodes where belong to the same group in different applications. We have also seen the use cases where the leader election is done using the Zookeeper as an service. We have also seen the dynamic configuration aspects of Zookeeper, and wherein multiple services are joining and some are leaving. We have also seen the status monitoring aspects as a service of Zookeeper, where it has monitored various processes and services in the cluster. We have also seen about the queuing aspect of this coordination service. We have seen barriers, we have also seen the critical section. So, in nutshell, wherever while writing the big distributed application for big data computations, these different services are merged together, are collected together, and is being provided by the Zookeeper. So, writing application, building application with Zookeeper is going to be very, very important, and we will see in the further slides how the Zookeeper is used in different applications for realizing these services. Thank you.